How many of you saw Neil's functional thinking session earlier? A couple of you, okay. Oh, by the way, introductions, that's me. Most people don't care. Moving on. How many of you have used Scala before? Couple hands. How many of you are familiar with design patterns? Okay, let me rephrase that. How many of you are familiar with design patterns in a manner other than I cut and paste code from the Gang of Four book? Okay, all right, cool. Because what this session is kind of intended to do is to help you start thinking in Scala. To help you start trying to reason, instead of, like when you learn a foreign language, right? And there's a certain level of mastery when you have enough vocabulary words to be able to say, where is the bathroom? And please, no squid on my plate, right? And then there's a level of mastery where you can actually put together complete sentences. Hello, how are you? I'm fine. And you can actually understand the responses that are coming back to you. But then the next level of mastery beyond that is when you actually think in that language, right? When you find yourself, when a response comes in, when a question comes in, you don't have to translate it into your native tongue, generate the response you want, and then translate it back into whatever tongue you're trying to speak towards, right? They say actually that you know that you have achieved fluency in a language when you dream in that language. Now, are you going to go home tonight and dream in Scala? God, I hope not, because if so, there's probably less hope for you than there was even just 5 minutes ago. But that's really where we want to go, right? That's really where you want to be able to take your knowledge. Just knowing the Scala syntax doesn't really give you a whole lot. It's when you start exploring some of the concepts, it's when you start exploring some of the ideas. And in particular, let's be really clear about this, Scala is not just a functional language. There are a number of functional languages in the world. If you want to play with a language that is just functional, I'll encourage you to go look at Yeti, Y-E-T-I, right? The name of the abominable snowman. It's an implementation of standard ML running on top of the JVM. And it's just purely a functional language. If you want to just kind of go grok the functional world for a while, you can go play with that and still be able to, produce jar files and blah, blah, blah. Scala is a hybrid of both the object world and the functional world, okay? And so it's really when we start drawing from both worlds that really is where we see a lot of the unique power that Scala represents. Scala has a cousin, by the way, over in the .NET world called F#. And I have a friend of mine who, even though she's a Java programmer, kind of got interested in F# and kind of started playing with it, toying with it, etc. And she actually, jessitron.com, if you go to her blog, she's got an example of how her Java code improved because she wrote the pseudocode in F# first. And then said, okay, now I know what I want to do. Now I know how I want to approach this. And then sort of translated it back into Java because, of course, Java is a very poor object functional language. It was designed to be an object language. Scala is the most logical equivalent to F#. If anything, F# is a little bit more on the functional side and Scala is a little bit more on the object side. It's when we take these two and combine them and start investigating that we really start to see some of the power here. Now, this particular session, I'm assuming that you have at least some familiarity with the Scala syntax. And I think one of you raised your hand. So the rest of you, you're just screwed. I'm sorry. It's not my fault. You didn't meet the prerequisites. Don't take it out on my eval, all right? It's your fault. You deal with it. I think you could still be able to grok some of the concepts, and I think you'll still be able to see some of what we're trying to get to, but obviously having to ask, what exactly is that square bracket there, slows us down, all right? So try to, the syntactic questions we can try to address later, and certainly, the examples will still stand for something for you to pick up later as you pick up more of the Scala syntax. But going into some of the functional ideas, part of the idea, and I'm just going to blow through these pretty quickly, because A, a bunch of you went and saw Neil's talk, so this will be repeat, and B, because, quite frankly, I want to get to the other stuff. This is foundation, prerequisite, etc. The functional world says essentially that the statement x equals x plus 1 is fundamentally busted. I mean, think back to your math classes. Think back to your algebra. Now, for some of us, that's going to be a lot longer reach than others of us to think back to when we were in grade school and learned algebra. But bear with me. The mathematical equation x equals x plus 1. Think about that for just a second. Remember what you do in math, right? Is you drop a value in for x and the equation should hold. And so if we drop the value 4 in for x, what do we get? We get 4 equals 4 plus 1. 4 equals 5. Folks, this does not work unless you work for Enron or you're part of the Greek government. Oh, come on. That was topical and funny. Yeah. Anyway, 4 equals 5 makes no sense. And the mathematicians of the world will be very quick to point that out. Now, we as computer scientists understand that x equals x plus 1 is not intended to try to be an equation. It's intended to be a sequence of steps. Fetch x, add 1 to it, store back to where we had x, right? But the interesting thing is if we look at the mathematical parts of this, there are some interesting concepts that emerge out of this. For example, reaching back even further, and this is probably going to be more of a challenge. Do you remember in algebra 2, 2 equations, 2 unknowns, right? Where you have x plus y equals 5, x minus 1 equals 2, solve for x and y. Do you remember how we did it? We isolated one of the variables on the other side of the equality sign, right? So x equals y, blah, blah, blah. And then we could take, once we had x equals something, because equality is equality, right? Means I can substitute one for the other. Then I can take that other and drop it in wherever x was, and suddenly now we have one equation, one unknown. We can solve, blah, 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 and get to answers for x and y. It's that substitutability that's really interesting. Because in the functional world, when we start talking about doing this for programming, this is where we get some of the lazy evaluation characteristics you hear about in Haskell. If we say x equals this plus that, well, we don't have to actually evaluate anything until we absolutely have to. And if that thing happens to be made up of other things and then made up of other things, and that substitutability also means then that we can do that anywhere that x is, anywhere it appears, etc. We have some really interesting concurrency properties that begin to emerge. If x is equal to this expression here, well then technically we could take the parts of the expression and fling them off onto other threads for calculation because x depends on all of them. And suddenly concurrency isn't nearly as hard, particularly because x never changes, right? At no point in math does the value of x ever change. We might derive a new value from it, at which point we call it x prime, but it is immutable. At no point does evaluating x change the value of anything else. These are properties that are really, really useful for when we start trying to program concurrently. And in case you hadn't noticed, concurrency is kind of becoming a big deal. Because our processors are not getting faster, we're just getting a lot more of them. How long before your phone has 8 cores in it? Your phone, 8 cores. Think about that for a second. You can't even program the phone, embedded devices, in a singly threaded manner anymore. So this is part of the reason why this functional stuff is getting really, really interesting and exciting. And some basic functional concepts we see, functions as first-class values, that's one of the key things that makes a language functional. Can I pass a function around as if it were just any other datum in the system? Right? Do I have function literals? Because remember, int x equals 1, well, x is now a value, but 1 is the literal representation of that value, of that integer type. Why can't I have function literals? In Java, we've been able to pass around functions as first-class values, but in a very, very cumbersome manner. We've always referred to them as anonymous inner class instances. Every time you created an anonymous runnable, you were creating a function literal, but you were doing so in quite possibly the most obtuse syntax ever invented. Java 8 will fix that. We are getting lambdas. Yay! Thank you, God and Brian Getz. Not a lot of difference between those two, actually. And this will help change a lot of how we program. Now, there's a bunch of other things that we see too. Strongly typed type inference, right? Functional languages like to have very rich, very powerful type systems. If you're not up on your type system theory, you're probably going to run into some really, really confusing error messages. And that's probably one of the weak areas of the functional world, is the fact that they assume that everybody knows what a catamorphism is. They can describe category theory, and we all dream in monads. I do none of the three, okay? And that's one of the areas where the functional community has to kind of step out of its academic background and meet the rest of us halfway. Immutable values, strong emphasis on recursion. Everything is an expression, not a statement. So in a functional language, again, based on its mathematical background, everything yields a value. So for example, in Scala, if else yields a value. So you can say return if true 5 else 7. Because that yields a value. It either yields 5 or it yields 7. Okay? That's a subtle shift in thinking, but it is an important one. Tuples, lists, we see lots of lists, vastly preference lists over arrays. For reasons we'll get into later. Pattern matching is basically a switch on steroids. Currying, partial application of functions. This is doable because if I have a function and we treat it as basically a function, we treat it as a first-class citizen. Suppose I have a function that expects 3 parameters and I give it 1. What's the result of that? The result of that is obviously a function expecting 2 more parameters. In Java, it just wouldn't compile. But in a functional language, we say, oh, okay, you've put 1 parameter there. Well, now go ahead. Now the result of that, because remember, everything yields an expression, yields a value. The result of applying 1 parameter to that function is a function that's expecting 2 more parameters. And you can call that just as if it were a standalone first-class entity. That takes a little while to wrap your head around. Trust me, it's taken a while. And my head is probably thicker than yours, but still. So again, first-class values, right? If I need to be able to, for example, iterate through a collection, historically we've always said get an iterator and use that to get each element out of the collection. That's just dumb. Why should I have to worry about having to get that iterator? Why don't I just pass the function into the collection and let it figure out when and how to call my function that I want to do on each one of these collection elements? This is called inversion of control. You may have heard of it. Right? Seriously. It's the don't call me, I'll call you principle. It's exactly the same idea. This is part of the reason why Fowler really wanted to move away from the term inversion of control and more into dependency injection for talking about, database connections and so forth being handed into you. Inversion of control is a generic principle. It can be applied in a lot of different ways. So instead of you saying, I want to grab every element out of this list, the collection could do that for you because the collection has better knowledge of how the collection is stored internally. And let's think about this for a second. You want to walk across an array list. You want to walk across a list, a linked list. You want to walk across some list that's somehow a mishmash of both. In each case, you're going to grab an iterator, and you're not going to be able to take advantage of, again, some concurrency opportunities. If you're just walking across the list and printing out every item in the list, do all of those have to be done sequentially? Is there any reason why the collection couldn't say, you know what, I've actually stored this collection in 4 distinct chunks, so I'm going to spin off 4 threads and have your function evaluate each element across those chunks in parallel? And by the way, what does your code have to do to take advantage of this? Nada. Just hand in the function. Let it worry about all the details. Once we see this idea of functions as first-class values starting to permeate through the rest of the environment, we're going to see a lot of really interesting things emerge. And that is one of the things that Java 8 is supposed to bring to us, is the idea of promoting this function as first-class value. Because now that we have lambdas, we can start to thread that into the rest of the library. And there's some other interesting features that are coming as a part of 8 that will help make that easier to do without creating chaos. Strongly typed, type inference, I mentioned this. Immutable values, recursion, mentioned this. Expressions, not statements. Mentioned this. Tuples. A tuple, think about a tuple as basically an object without field names. No methods, just data. And if you look at what we do in Java, for example, if you look at data transfer objects, right, and everybody talks about how you write a DTO and it's got some fields, and there are some people who even argue that you shouldn't even have getters and setters because you're not really trying to encapsulate anything. DTO is a tuple, guys, or tuple, depending on how you want to pronounce it. It's a tuple. A result set is a tuple. It's basically a collection of data, a bundle of data that is essentially just ordered, right? So if you say I want a tuple of string, string, int, then okay, here's a tuple of string, string, int, and what that string, and that int mean is entirely up to you. There's no field names there. There are a lot of places in Java where we could, in fact, use tuples quite elegantly, quite strongly, quite well. Lots of people are really, lots of object purists don't like tuples because A, it's public data. Oh my God. A field in the public space. Didn't God have a commandment about that or something? At the end of the day, if you're not, we need to be more clear about what we're trying to encapsulate and what we're not trying to encapsulate. A DTO has no encapsulation whatsoever, does it? If you change the representation of the DTO, doesn't matter whether the fields are public or private, everybody in the world who touches that DTO has to recompile. That's not encapsulation. That's just annoying. There are places where tuples are extremely useful. Lists are highly used, strongly used inside of a functional language because lists can peel head and tail off very, very easily. You'll see why this becomes useful in a second. Pattern matching. Pattern matching, imagine switch case, but where we can also extract values out and store them into local variables while we're working at it. Imagine being able to switch on things like the type of, along with things like, hey, by the way, switch when this particular value in the tuple is equal to this string, switch when it's on this particular string. If you go look hard at pattern matching in Scala, when you come back to Java, you will feel like a kid whose Christmas has been taken away from you. Okay? Pattern matching, in many respects, is the gateway drug to getting you to want to use a functional language. Because there are if you told me that I could have a programming language with only one kind of flow control construct in it, I would take pattern matching and I wouldn't miss the rest. Okay? It's extremely, extremely powerful. It's switch case on steroids, except these steroids won't, kill you. Partial application, I mentioned that, providing some of the parameters, but not all of them, to reveal a new function, expecting the remainder of the functions. And currying, well, it turns out that once you understand partial application, currying is a form of partial application that says, you know what, I can take a function expecting a couple of parameters and provide one, and then use that as the input to another one, which is the input to another one, which is the input to another one, to create a pipeline. That's officially known as currying. And in laziness, again, this is part of that mathematical representation that says, look, I don't need that half of the equation, so therefore I'm not even going to bother calculating it. In some respects, we see some of this style of laziness when we look at Boolean short circuit evaluation, right? If false and doesn't matter what the rest of it is, because the false will render the whole thing irrelevant, so we don't even evaluate the rest of the expression. But we can do that in a functional language by simply saying, look, I'm not going to call anything until I absolutely have to. I can pass that thing around as many times as I want, but it's not until it's actually necessary that I will go evaluate it. And again, this provides some opportunities for concurrency and so forth. One of the other things that we see show up in a lot of functional languages, although this is not specifically a functional concept, is this notion of a sequence. So we have these lists in Java, right? So I have a list of 1,000 elements, and what that means is I have a list of 1,000 elements. In a functional language, for example, Haskell has this notion of an infinite list. And this really blows people away if you come from a C++, Java, C# background, because you're like, how can you store an infinite list? How can I have a list of 1 to infinity of all the integers ever? How would I represent that in memory if I have a finite amount of memory? And the way this works is functional languages actually don't store the entire thing. They just know how to manufacture the next element in the list. This is sometimes known as a sequence or a stream. And we can look at a lot of things as a stream or a sequence. And doing so opens up some really interesting possibilities, particularly when working with iterators and so forth, being able to pass something in. So this, for example, is where the groovy guys get all excited because they say, look, just hand a function into the file class, and we will go ahead and call that function on every line in that file up until that file ends. Even if that file never ends, we'll just wait for the next line to be there, and then when that line is there, we'll hand it to your function and you can keep going. This tweaks you in weird ways because now all of a sudden you don't think of the entire list having to be in memory anymore. I don't have to read. In traditional Java, I had to read the entire file into memory, put that into a collection, and then iterate through the collection if I wanted to make use of any of the collection style interfaces. But you don't. As long as the collection, the sequence, knows how to get the next thing, you only have to have one of those things stored in memory at any given moment in time. And you just process each on an on-demand basis. And you go, ooh, lots of places where we can look at things as a sequence. Okay, patterns. There are a number of reasons why patterns came to be, right? How many of you have read the Gang of Four book? Come on. The Gang of Four book, design patterns, right? It's been so long ago you've forgotten. This was required reading for anybody in the Java space, like 15 years ago. If you walked into a job and you said, what's the Gang of Four? You walked right back out of that job. You were done, right? And so one of the things that I found difficult, frustrating about people in the functional community is they kind of poo-poo the whole idea of patterns and so forth. It's like, patterns, bleh, who needs those? Let's talk about catamorphisms. Okay, stop. Anytime you're learning something new, it helps to take what you know and see how it translates into the new world, right? Even if it's not necessarily a direct correlation, it still helps to be able to start from something you know, because it gives you some place to sort of anchor, gives you some concreteness. So, for those of you who've forgotten who the Gang of Four were, right? This is the Gang of Four, Gamma, Helm, Johnson, Felicities, wrote a book back in like 1994, which probably was before some programmers were born at the rate things are going. And they broke their notion of patterns, these elements of reusable, object-oriented concepts. They broke them up into three distinct categories, creational, structural, and behavioral, and said, look, this is kind of how, we see these ideas occurring over and over and over again in software, in object-oriented software. And it was the genesis of the patterns movement. There was actually a book called The Gang of Five, which predated them by about 6 months. But for whatever reason, this one really tapped into the angst that a lot of not Java developers, C++ developers at the time, it tapped into the angst that they were feeling like, I don't understand this object thing. I don't get it. I don't understand how I'm supposed to use these things. What's an object? Now, the interesting thing about this is, if you look up there, nowhere do we see anything about domain classes. The whole domain-driven design is completely absent from this. The early days about objects were about building infrastructure and support code, and completely antithetical to the way Alan Kay imagined objects to be. But be that as it may, extremely influential in terms of how people looked at object orientation. So, one of the most popular patterns from the Gang of Four is, of course, the singleton. Ensure a class has only one instance and provide a global point of access to it. I think every Java, C++, C# developer has written a singleton at one point in their life. All right? Now, interesting and ironically, we've been doing singletons for a lot longer than the Gang of Four. It's just that before then we called them globals, and they were bad. Now that they're singletons, they're good, right? Kind of like how, before it was, police brutality and Big Brother, and now it's the Patriot Act, right? Come on, guys. I know it's after lunch, but this is my A material here. Come on. All right. In Scala, we could do a singleton just by using the object keyword, the end. I mean, literally, you say object foo, you have a singleton. The end. We're done. This is interesting because a lot of times what happens is yesterday's concepts that require a bunch of code to support become today's first-class citizens. We could do objects in C. It was not hard. As a matter of fact, if you did 16-bit Windows C programming, you were programming in object-oriented style. You were sending messages. You were doing objects the way Smalltalk does objects. You were sending messages. You were receiving these messages, discarding the ones you don't want. You had this thing where data was stored. It was called the HWin, the window handle. You were doing object-oriented programming. It just took you 20 pages of code to do it. And C++ came along and said, you know, we can make a lot of that code go away. And we all went, hallelujah, praise objects, right? Well, some of these other concepts came along as objects slowly began to mature, and slowly we began to find where the limitations were. And we said, you know what, it would be really cool if we can have an object that was all by itself out there. And we call it a singleton. And that turns out to be kind of useful. So Scala said, great, first class construct in the language. Object foo, you're done. Now define whatever methods you want on it. By the way, when you have singletons, do you still need statics? This is one of the interesting debates that rage within the Java space, right? If I want to have only one of something, should it be a static field of a class or should it be a singleton instance? Scala makes that very easy. It says there's no such thing as static. There are classes of which we have instances, and then there are objects of which there is exactly one. The end. And there are instance methods on the singleton, and there are instance methods on the instances. The end. No more debate. No more discussion. It's silly. It's stupid. This is how languages advance. This is how we move to the next step. A lot of these patterns are going to disappear because the languages say we want to make that a first-class concept. So here we see a singleton. That was exciting, huh? Moving on. Command. Encapsulate a request as an object, thereby letting you parameterize clients with different requests, queue or log requests, and support undoable operations. Right? The example that they used in the Gang of Four book for command was menu actions. Right? You know, if you're writing a text editor and you want to be able to undo everything you just did, well, what they said is each menu action, each keystroke, anything you do inside the editor should be a command object. And then the command object should be stored in a queue, and that way you can know exactly what you were supposed to do. The command objects get handed, you know, when you click on the button, that command object gets fired, and the editor, controller, whatever you want to call it, executes the command to see what happens. A new character goes there. But we can also keep these command objects in a list, in order, so that as the user says undo, the command object knows how to undo what it did, which is a very useful construct. We actually see this resurfacing today, by the way, in larger systems, what's known as event sourcing. So the idea now is, okay, I have a state of the universe. I have my database. And instead of user does something on a web page, triggers a change to a row here, user doing something on a web page triggers an event which says, by the way, the user changed this table, this column to this value. And instead of making the change to the database, we just store that event somewhere. It's very, very similar in some respects to how we see source control systems work. We start from a known state, and then we just have a bunch of deltas. And then at a certain point, you can snapshot and say, okay, the deltas, you know, we'll still track all the deltas, but this is what the current state of the database looks like, and then we'll just start tracking deltas again. This is known as event sourcing, ES. All of this is basically based around the concept of the command pattern. Here is a small nugget of thing that says this is what you do. And do you know what we call that in a functional language? A function. Any questions? I mean, again, this is a case where we may put a small amount of doctoring around it because one of the consequences, one of the context of command is not just we want to do, but we also want to undo. Okay? But within Scala, any object which has a method called apply can be directly invoked. So I can take this calc command, right? So you see CMD here in the corner, right? This guy here, it's a calc command. The name of it is add, and the function, again, here we see the function literal, which says x and y are two parameters of both of type int, and the expression here is we add the two, right? And again, because everything is an expression, that implicitly is what's returned. So now when I come here and I say command parens 2, 5, that is Scala syntax for saying invoke the apply method. on that object. Any object can have an apply. Your person can have an apply. So that you could walk up and say, Ted, parens, something else. Whatever that makes sense to you. What do persons do, right? It's a do kind of operation. It's an implicit do. So creating a command is just as easy as object with an apply, the end. Now, to support the undo, we would need to write some other kind of method which would maybe be unapply, which Scala won't recognize. But again, that's us taking the first-class construct in the language and filling it out to be the pattern, right? So a command wants to be able to do and undo. Okay, we would still have this command, we would have an apply, we would have an unapply, and we could string these things together and then roll them back as we needed to, okay? But again, the concept of a thing that knows how to do something, we call that a function. Strategy. Define a family of algorithms, encapsulate each one, and make them interchangeable. Strategy lets the algorithm vary independently from the clients that use it. Kind of sounds familiar, doesn't it? Right? A lot of these patterns tend to be slight variations of each other. And you know what we call a strategy in Scala? A function. Matter of fact, in a lot of cases where we look at the gang of four, once you have functions as first-class values, a lot of the patterns just turn into usage of first-class construct, the end. Doesn't mean the pattern is any less useful. It just means that we're not going to be able to, ascribe quite as much mysticism to them as we're used to. Oh, visitor, that's like the hardest pattern in the whole book. Yeah, and it turns out to be really kind of simple in any language which supports double dispatch directly, like Lisp. Composite. Compose objects into tree structures to represent part-whole hierarchies. Composite lets clients treat individual objects and compositions of objects uniformly. In other words, it's the classic tree, right? It's the classic node leaf tree. Directories and files and so forth, right? A directory is a file, but also contains files which can be directories because a directory is a file. It's a classic tree in object orientation. And in Scala, we can do this. It's actually pretty straightforward. We can see the abstract class there across the top, drawing element. You can see it defines one method called draw. We can see the primitive drawing element. Notice it has a draw implementation. We can see the composite, which says, by the way, I'm just going to take a list of drawing elements. And when I draw, now notice what I do here. Again, list is a collection. The collection knows best how to iterate across it. So what I do is I pass in this des.forEach parens d arrow d.draw. That is me handing a function literal into the collection saying, do this on every element. Okay? And of course, what's going to happen if one of those children is another composite? Well then, when its draw is called, it will in turn call draw on all the subtypes as well. Get really used to that concept because when Java 8 ships, as far as I know, what Brian has told me his intentions are, all of the collection classes will have similar kinds of methods. So instead of obtaining an iterator from an array list, you will say array list.forEach and pass in a lambda. And it will be a hell of a lot shorter and a hell of a lot easier. Because you're saying, I don't really care about the rest of it. Just here, do this on every one, we're done. Okay? Now, Scala brings in a couple of new ideas too. Wouldn't be interesting if it didn't. Scala was just another variation of Java. Who gives a crap, right? Let's just all go home. Or better yet, let's go to the bar and have a beer, right? Scala brings some new concepts into the game here. Now, one of the things to remember is that the patterns community says it's not a pattern until it shows up independently 3 times. And then technically it has to be workshopped at a patterns conference. Now, that was what they said 10 years ago when pattern workshops were available like in every part of the country. I don't know if they still hold to that today. But the point is, it's not a pattern until it has been independently discovered in 3 entirely different places. I'm not suggesting these are patterns per se. I'm suggesting these are ideas that I've seen, and they might qualify as patterns, they might not, I don't know. Decompositional recursion. See, one of the things is when you stand up here on stage, particularly when it's on a real stage, you have to use pretentious sounding language, otherwise people won't take you seriously, okay? Decompositional recursion. You've got a list of items, you want to do something to each one as you do it. The list itself, however, is immutable, as are the items inside of it. So what you want to do is basically peel off the item at the head of the list, do your operation to that, gather the result, and recurse on the tail of the list. The head of the list is the one item, the tail of the list is everything after that. This is an extraordinarily common pattern in functional languages, and part of the reason is because it is completely thread safe. The list is immutable. Lots of people can be doing things to that list at the same time because it's immutable. And the items inside the list are immutable. And all of your intermediate state, all of the intermediate results as you go, they're not stored someplace else. They're stored on the thread stack because we are recursing down. When we get to the end of the list, we'll start peeling it all back together and turning it into a new list and handing that back. But it's all scoped to this thread. Zero concurrency concerns. And people in the audience are like, ooh, I like that. No thread concerns. Now, most languages have this construct already. They call it a fold. Fold left or fold right. Whether you want to start from the head of the list and work to the right, they call that a fold left. Or whether you want to start from the tail of the list and work left, they call that a fold right. Don't ask. Just, it's going to be backwards either way you want to look at it. Some of them call it fold head and fold tail, which makes more sense. Some of them call it L fold, R fold, whatever. Because the whole idea here is we're taking two elements and sometimes we're folding them together to do, like, if we want to add up all the elements in the list, we're folding them into a single value. In other cases, it's known as just a map, because I want to map a function onto that individual value and produce a new one, et cetera, et cetera. But here you can see what I've got. I've got a list of string here, and what I want to do is I want to reduce it in some fashion, right? And so here I'm using the reduce list. This reduce list function here. You'll notice this L match curly brace, that's pattern matching. What I'm saying is, let's look at L, which is the list that's passed in. If it's the empty list, just return an empty string. Okay? That's the exit case. That's when we stop recursing. This sort of decompositional recursion always has to have an exit case. Otherwise, it's known as an infinite loop. Generally, not a good thing. Okay? But the second case here, you see this case it, : list? In that expression, I am saying it is the head of the list. I'm literally peeling these two apart. And so if the list is an element of one or more, that first head element will get bound to the local variable it, and the rest of the list will get bound to the local variable lst. And then what I do is I say, well, in this case, again, because everything is an expression, pattern matching is an expression, what I'm going to return here is it, that head of the list, plus recursively do this to the remainder of the list. So what this does is it takes a list of strings, A, B, C, D, as 5 separate strings, and smashes them all together to be A, B, C, D, E in one string. I'm folding them all together into one return value. Make sense? You see this pattern a lot. And this is part of the reason why we like lists, because we like peeling off the head and doing something with the tail and storing it on the stack, storing the head on the stack until we get to the end of the list and then pushing all those head parts together back into a single list. No, by the way, it maintains the order as well and good stuff. You can see we can also do this with integers as well. In this case, I pass in the exact operation to do. So I've got a list of numbers that I want to add. So I say I want to take my list of numbers and call my fold here, passing in 0, which is the starting value, the operation to do and the list to do it on. Okay, and down below, we see using Scala's built-in fold left. These two will produce the exact same result. So far, so good? By the way, one more interesting thing about this is also how we can turn a list of objects into a stream of XML. Because think about what we do when we want to take a collection of objects and turn it into XML. We go to each element in that collection, let's call it a list, and we say, start with this seed. We'll call that a starting value, a seed value, and do this to produce this result.
This is exactly the same thing we did with the list of numbers in the previous slide. And the operation used to produce each person's XML is just, hey, return this string, right? Return this person, first name, person in XML format. The fold is not just for doing trivial exercises for adding numbers together. It's for any time you have a collection of anything that you want to reduce down to a single value. Now stop for just a second and think about this. If you had walked in here and I had said, I'm going to show you a technique in Scala that will be generic across both adding numbers together and turning complex objects into XML documents. You'll use basically the same built-in constructs to do both of these operations. How many of you would have believed me? And do you know why? Because the functional way of going at things is completely antithetical to the object-oriented way of going at things. And this is a good thing, because it means that when we have both axes covered, we have all kinds of opportunities for reuse. What you have to do, though, is you have to stop thinking in object terms and start thinking in functional terms. Not because I want you to stop thinking in object, but because you have to open yourself up to the possibility that there is an entirely different dimension of reuse here than what you're used to. Once you start thinking in both directions, now all kinds of interesting possibilities begin to emerge. And your code will get shorter, tighter, cleaner, easier to understand, etc. But only if you understand that additional dimension. For years, the object community has said, hey, there is no such thing as color. There is black and white. And I'm trying to tell you that not only are there shades of gray, but there's this concept of blue, red, green, etc. It's going to take a while to let your eyes adjust. Once you do, though, you'll start to see that not everything has to be these cross-hatched patterns of black and white. Now we can start throwing colors into the graphs. It's going to take some time to get that depth into your way of thinking about how we do software. The iterator inversion of control. We talked about this a little bit. But one of the dark secrets that the guys in Java, the guys at Sun who now work at Oracle, one of the deep, dark, hidden secrets that they don't want to tell you is that every time you create an iterator, God kills a kitten. I'm not joking. I'm not joking. It's a dark, ugly secret, bound up in ritual and you know, the Sun buildings, right? They burned them down because they don't want you to see the pits in which they conducted these rituals and bound the source code together. Now, you guys like kittens, right? Is there anybody here who does not like kittens? I should have known. The guy from Oklahoma City doesn't like kittens. Okay, in your case, God kills a puppy. Oh, God, in that case, it's 2 kittens or 2 puppies that die, right? The point is, I want you to stop reaching for iterator every time you want to go through something, because there's a lot of benefits to be had by letting the collection worry itself about how to do the thing you want to do. Instead of reaching for an iterator to walk across the collection, create what you want to do as a function, as a block of code, and hand that into the iterator. For 2 reasons. Number 1, because when you write it will actually be much, much shorter, and you won't have to worry about a lot of weird edge cases. But also, number 2, your code is intrinsically more reusable. Because what's the drawback to a for loop? You can't reuse a for loop. Attempts to do so will lead you to this pattern. Plus, we get the idea of doing this stream-like behavior as well. How many of you have seen the Groovy demonstration where they pile you into a room and they say, Groovy is better than Java, and you go, no, it's not. And they say, yes, look, because if you just want to read a text file, look at all that crappy code you have to write in Java. And in Groovy, it's like 2 lines. And the idea is you're supposed to go, you're right. Groovy is better than Java. I'm so ashamed. Stop. The only reason why they can do that is because they took all that crap code and they baked it into their library. You can do that. And you could do this exact example in Java, by the way. It is very easy to create a file line iterator. Now, I'm doing this in Scala, but basically this code here, right, this file reader, buffered reader, et cetera, et cetera, et cetera, this file class that has this elements, blah, 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 this is actually just collections 101. It's collections 101 and file IO 101. But notice what I'm doing here. I'm not reading the entire line, the entire file into memory and storing them as lines in a collection. Because then if this is a 2 gigabyte text file, I blow out the JVM's heap. Instead, what I say is the iterator knows, every time you call next, the iterator knows how to go fetch the next line. So all it has to do is know how to manufacture the next element in the list. So that now down here I can say, hey, I want to create one of these, and then, because in this case it extends the iterable interface, right? By the way, that interface exists both in Java and in Scala. In Scala, it has some additional methods to it that are not present in Java, but they'll probably be there as a part of Java 8 when, now, because it's an iterable, because it satisfies the idea of being able to create an iterator, I can say for each line, do this. And again, you can do this in Java. You just have to put it into a jar file and use that as part of your standard library. There's nothing Scala-esque about this. This is everything about thinking functionally. And then the next time one of those Groovy guys comes by and says, Groovy is so much better than Java, you can say, fuck you, Groovy, get out. You just have a more interesting library. This is not baked into your particular language. And I'm not bitter. I'm really not. I'm really, really not. Pipelining. This is, again, part of that notion, this concept of currying. The idea that I have a set of behavior I want, but if I've got actually a lot of these behaviors that I want, and there seems to be just so many things that are common across a lot of them, right? Think about like mathematical operations. Everything we do in math is basically built out of the 4 or 5 cardinal operations, right? Add, subtract, multiply, divide. Technically, modulo is in there as well, right? Everything else is kind of built up out of those. It would be great if we could somehow string them together, put them together in kind of a modular way. Well, this is where we get into this notion of partial application of functions, currying. So here I have 3 functions, convert to int, double it, and square root it. And implicitly, they each take 1 parameter, okay? And now, using the built-in Scala and then, this is a method that says, oh, if you give me a function on the right-hand side, I will take the function on which we do this. I'll return another function that says when you call it, it goes to A and then to B. In other words, it's the glue that joins these guys together. So now the pipeline is convert to int and then double it and then int to double and then square root it. Now, just tell me that if you presented that pipeline definition to somebody who's not a programmer, they won't understand it. This is where we start getting into the DSLs thing, right? The idea of a domain-specific language that I can give to non-programmers and let them define the behavior. And if you think about it, this is all of what that business process modeling crap was about. This is what BizTalk was supposed to do. This is what Oracle BPEL was supposed to do. It's just basically define these workflows, define these lists of things so that non-programmers could maintain them. So what we do is we build the small primitives, and then they join the primitives together in interesting ways to create business behavior that programmers don't have to maintain. Winning. Expando meta object. Occasionally we want objects that are actually manipulated, defined, maneuvered, etc. at runtime, right? We don't want to know all of the properties. We don't want to know all the behaviors. For all that the functional community loves strict typing, there are still a lot of cases where it can be helpful to have objects that change their shape and change their behavior and so forth at runtime. The Lisp guys are squarely in that conjunction of forces. The Lisp language is a dynamic language that is a functional language. Okay? And believe me, if you ever want to see 2 functional guys fight it out, have a Haskell guy and a Lisp guy argue as to whether or not Lisp is a real functional language. And they'll just beat the crap out of each other. That's kind of like asking a group of C, C++, Java, or C# developers where the curly braces should go. It's bloody, it's ugly, and it's really kind of pointless, but so be it. We can do this because, hey, let's just use the built-in Scala map, and notice here, dyne1, it is an object. Tell me how dyne1 is different from a traditional Java class. We have fields, first name, last name, and age, and we have methods. We have this thing called toString, which, by the way, the value is a function which knows how to do something with this in order to produce a string. You want to hear something else? That's JavaScript. That's exactly what JavaScript does. JavaScript is, the objects in JavaScript are nothing more than a bag of name-value pairs where the values can either be data or code. The end. That's it. That's the secret to JavaScript. Now, unfortunately, using this is kind of a pain in the ass because Scala is type-safe. And so when I say that this is a map of string to any up there on the first line, it means that in order to take toString and see it as the function that takes a map of string to any and produces a string, in this particular case, I have to do this really ugly downcast. Blech. And to be honest, most of the time we don't want completely dynamic objects. What we want are objects that have a core set of things that must be there. So think about persons for just a second, right? Think about people. We've always talked about various ways in which we model the world, right? How many people in here speak French? How many people speak German? Chinese? Russian? Okay, how many people in this room cook? How many people in this room play soccer? How do we model your skills at all these different things? We can get into this, well, you know, we have skills and there's a name of the skill and it's kind of a, you know, a numeric value or something like that. But if we go drilling deep enough into each one of us, there are going to be things that each of us know or can do or like to do or have or don't have, right? Ergo, thinking about, for example, the surfer girl who lost an arm to a shark attack, is she still a person even though she has only one arm and two legs? Is she still a person if she has no arms? And yet there are a lot of things that she can't do. She's still a person. See, object modeling in this really, really strict type-safe manner breaks down at a certain point. Every person has a first name and a last name. Yeah? How about Bono? How about Sonny and Cher? How about the artist formerly known as Prince? Dude has no name. He has an icon. Is he still a person? He's more of a person than Michael Jackson ever was, right? Our modeling breaks down in weird edge cases. And so in some cases what we want to do is we want to have a solid core. Person has a first name, last name, and an age. But then maybe they also have a does business as. They have different attributes which are not common across all persons. Historically, we've always said those should be subclasses. But subclasses are a code time, a developer time construct. And not all of those are visible at the time that we model this thing. So occasionally what we want is something that has a core set of data, but then also has some expansive capabilities, right? So we can still say, all right, look, this expando is actually something that inherits from hash map. And, well, we still have the casting problem here. Or, you know what? What I'm going to do is I'm going to say that a person has a first name, last name, and an age. But in fact, how the person wants to represent their string representation, because I think if we go back far enough, Bono does have a first name and a last name. So maybe the way we represent his name to the rest of the world is different, or the way he self-identifies is different. So here, what I'm going to do is I'm going to say that there is another value on person called toString impl. And it is, in fact, a function. And that function is mutable. So we can plug in different representations of how to generate this toString on an instance-by-instance basis. And we do so by changing toString impl to something else. And the default toString, which the rest of the framework has expected, just defers to that variable functional behavior. In other words, we can be static where we need to be and dynamic where we want to be. Which, if you think about it, makes more sense than all static or all dynamic. The selfless trait. So the idea here is we want to be able to create some services that people can just consume, but not necessarily having to do so by being really, really explicit and verbose about it. So, for example, we have this behavior called greet, to be friendly. Hi. And we want this to be something that anybody can do. So there's two ways to do this. Number one, we can extend the object friendly, which means we implicitly get the trait friendly. Notice that the object and the trait can have the same name. This is frequently done just because that way we don't consume more than one name. And so here, example app 1 extends friendly. But the other thing we can do is, because this is an object up here, object friendly, it means that when we import that object, all of its methods can be intrinsically statically imported as well. So that now I can say import friendly dot underscore, meaning that's kind of like the static import in Java. Grab all of the methods, because again, there are no statics in Scala. So grab all of the instance methods and make them available as top-level symbols. So that now, by importing friendly, I can just say greet. There is no intrinsic inheritance relationship between example app 2 and friendly, other than the fact that I'm just using the method defined in that trait. But people can also import it directly if they choose to, if, for example, there would be some sort of ambiguity conflict, because there's another class called Grumpy who also has a greet, which isn't quite as friendly. Okay? The drawback to the second approach is it's not nearly as clear where greet comes from. Because remember, there may be like 50 lines or 100 lines or 2,000 lines between the import and the actual usage. So in that case, doing the actual extends can be a little bit easier. Making sense so far? Okay. 2 challenges in the 0 minutes I have left. First challenge, we want to create a lottery, right? You guys know how the lotto works. You can choose numbers 1 to 49, and then every week or so, the random air ball thing pops those numbers up. 5, 6, 7, whatever numbers. But the key thing is you never draw the same number twice. So this isn't just generating 5 or 6 or 7 random numbers. It's generating random numbers within a range such that no duplicates will ever appear. That's the critical part of this. So write code to do this lotto thing. Now, just because we're short on time, I'll show you what the solution looks like. In essence, what I'm doing here is I'm saying, okay, I want to be able to randomly select this number of items from this range, right? From 1 to whatever that number is, okay? And I call random select. And notice that random select actually has a nested method inside of it to do the actual work. Why? Because we use that structural decomposition to say, hey, I need 6 numbers out of this list. And what I want to do is I want to generate a random number within that range and pull that number out of the list. And then take that remaining list and do the same thing again, and again, and again, and again, and again, until I have my 5, 6, 7 numbers, whatever. So what we can see there is we do random select, and then we random select R using that random object that's passed in. If the number that I need to get is 0, remember, we have to have an exit case. So that's when we return nil, and we don't continue to recurse. Otherwise, we remove the number that was randomly generated from the list, and then put that into a list of its own after calling recursively into the same method to generate the next number. Pure and simple decompositional recursion. Given an XML document, such as this, give me the total cost of these items. Okay? Now, one of the things, this is a little bit unfair, because one of the things, if you're not familiar with Scala, that you don't know is that Scala has some built-in syntax for being able to consume XML very easily. And the best part of this built-in syntax is it's not really built in, it's just a Scala library. So here, when I've got this data equals shopping, item, shopping, right? That's an XML literal, what Scala understands. But then the rest of this is all just straight library stuff. You see here where I do this for loop for item, arrow, data, backslash, item. The backslash there is essentially a small XPath query. And that says, give me the items that meet this particular XPath query. So it says, give me all of the item nodes underneath whatever the current node is. So the current node is shopping. So therefore, give me all the item nodes under there. Then, by the way, for loops aren't really loops in Scala. They're what are called comprehensions, and they're more like pipelines. And so this for loop takes the resulting items and hands them to the next phrase here, which says price is equal to item backslash the attribute priced dot text dot to double. Okay? So now I'm converting that price into a double value, and then grab the quantity and yield the result price times quantity. Now, how exactly does this work? Because essentially the comprehension does one of two things. It's either a generator producing more items to evaluate the final body against, or it's a filter saying this item can be passed on to the next stage or it's not. So what this does is implicitly creates a list. We find, first of all, the two items that have item there, and each one of those is going to get passed to price, which is going to produce the price element. And each one of those is going to be passed to quantity, which is going to produce those quantity elements, which means, by the way, that now item, price, and quantity are locals available inside the body of the for loop, where this body consists of yield, price times quantity, where the yield keyword basically says, hey, return this, but what we mean by that is plug that into the list that will be the result of this particular expression. The end. Do that in Java. I double dog dare you, because it will not be pretty. These are some of the advantages that Scala has over other languages. Okay? Scala is not perfect. Scala has some interesting quirks. Scala has some ugly quirks. Scala has some things that they need to fix. An error message coming out of the Scala compiler can read about like War and Peace does. In other words, completely incomprehensible, and it goes on for days. Okay? But for all of that, the reason they have those really, really nasty messages has everything to do with the strong typing, type system, category theory, blah, blah, blah. And the Scala guys know this. Martin has heard the fact that his errors are incomprehensible starting from about Scala 2.6. And they have been steadily working to make them more comprehensible. But you also have to meet them halfway, and you can't just use Scala like you've used Java or you're missing the point. You need to start thinking in that other dimension. You need to start thinking about reusing behavior, algorithms, in addition to trying to create these vertical trees of classes that are related in an inherent basis. A couple of resources for you. There's 99 Scala problems, which are similar to the two that I just showed you. How do I solve this? This is what it would look like in Scala. And by the way, these are not right. You could maybe come up with a more terse way of doing it. And whether terse is better or not, that's an aesthetic judgment, right? Code that you wrote is rememberable and discoverable by you. Code that somebody else wrote is sometimes too terse or too verbose. Let's just call it an aesthetic and go from there. There's also langref.org, which has a number of similar problems, but they actually show how to solve them across a variety of different languages. So if you want to compare Scala to F#, to Haskell, to Lisp, to Clojure, to Java, to C#, you can do so. And if you have any questions, I'll take them outside because we are officially done. Bye.